All right, guys, this one's not going to be easy. This lesson is kind of long. The material makes sense, but you really have to take your time and go through it. So this is technically our last test. Did someone say test? This is technically our last test. There is actually one more that will come that I'll go through next week. But this is our last big one, and this one we use a lot. Almost as much, if not as much, as geometric series test. So it's huge. You have to know it. You've got to take the time on it. Here we go. So we're going to finish the packet today. That means we have like 2 or 3 pages. Yeah. Get a cup of coffee, get out of bed, get yourself going. Here we go. So this last test is called the ratio test. And the first way we're going to see it is just like we've seen all of the other tests, where we're given a series, we're asked if the series converges, but the series won't be geometric, and the integral test and direct comparison might not be the easiest way to approach it. Direct comparison test and integral test are easy if you can immediately see how to use them. But if you don't see that something is like 1 over n to the third, then it's not going to be super helpful. So anyway, what we do for the ratio test looks a lot more complicated than it actually is. So if I have a series, I'm going to be finding the limit as n goes to infinity of the n plus 1th term of the series over the nth term of the series. You're going to say, what the heck are you talking about? Bear with me. I'm going to set up this ratio and look at the limit as n approaches infinity and decide what I get as a result. This won't be that hard. You'll be able to figure it out pretty easily. But the idea of the ratio test is whatever I get from this, which I'll show you how to set up in a second, the number that I get, if that number is less than 1, the series will converge. Or sorry, if the absolute value of the number. If that absolute value number is bigger than 1, the series will diverge. And if the number equals 1, the test is inconclusive. So it's a lot like geometric in terms of the answer that we get and how it relates to whether the series converges or not, right? When we had a geometric series, our multiplier that we called r, as long as the multiplier was less than 1, the series converged. If the multiplier was bigger than 1, the series diverged. The only difference is for geometric, if the multiplier was 1, the series diverged and we were done. Now, if this magical number that we're going to find equals 1, the test is inconclusive. And that's when you have to go use maybe the direct comparison test or the integral test or something. But what the heck are we talking about? So I'm going to be setting up this little ratio every time I do the ratio test. That's where it gets its name, OMG. So how I set this guy up is like this. So let me go to this example. You can still use the nth term test first. Make sure the bottom is growing bigger than the top. In this case it is, so that means I should keep going. This actually is geometric, so I could use the geometric test. I could look and see what the multiplier is, which is actually going to be 1 over e, and make sure that the multiplier is less than 1. In this case it is, so this would converge by the geometric test. But because it's a simple series, let's just show how I would set it up using ratio test. So the ratio test says I'm going to find, RT ratio test, the limit as n approaches infinity. And I'm trying to set this up. I'm going to plug in n plus 1 for any power or any n that I see in my series. So I'm going to find the limit of 1 over e to the n plus 1. And I'm going to divide that by the series itself. And I'm going to reduce this and see what I get. So to apply the ratio test, I am plugging in n plus 1 for all of my n's, and I'm dividing by the original series itself. Now I'm going to do some reducing. So because I'm dividing fractions and I really don't want to deal with that, I'm going to take this and flip it. So I'm going to have 1 over e to the n plus 1 times e to the n over 1. Just to make sure everyone follows, I'm going to pile this together, make this e to the n over e to the n plus 1. And now I'm going to reduce. So now is when power rules really come into play. Like, what do we do with exponents and stuff? So if I have the same base, but different exponents, I just subtract the exponents. So this becomes the limit as n goes to infinity of e to the n minus n plus 1. Okay, I'm just subtracting exponents. Be careful, I do need this bottom exponent to be in parentheses because I'm subtracting the entire thing. So I end up with the limit as n approaches infinity of, am I still in the square? Yeah. Of e to the n minus n, so that's 0, so negative 1. So what do I get? I have the limit as n goes to infinity of 1 over e. Well, what do I do with limits? I plug in infinity. Well, there's nothing to plug in. That means the limit of this is always 1 over e. My answer is 1 over e. So with the ratio test, we do all of this work. We plug in n plus 1 into our series. We divide by the series itself. We reduce our powers, and then plug in n to be infinity. Well, if the n's all canceled, then fine. What I got was 1 over e. And I compare this in this little chart. So 1 over e, is that bigger than 1 or less than 1, or does it equal 1? Well, e is like 2.7, so 1 divided by 2.7 is less than 1. So 1 over e is less than 1. So therefore, by the ratio test, what the number I got was less than 1, so the series will converge. So therefore, the series converges by the ratio test. That's basically how it goes. Now, there are ways it gets more complicated. Let's look at one other example that doesn't get too complicated before we get complicated. So our next example. Well, nth term test, which grows faster, a polynomial to the 10th or 10 to the n? Well, 10 to the n is going to grow way faster, so the bottom's faster, so the nth term test tells us to keep going. This is not geometric. The bottom would be geometric, but if I looked at the first few terms just for fun, I would have 0 for the first term. I would have 1/10 for the second term. Then I would have 2 to the 10th over 10 squared. Then I would have 3 to the 10th over 10 to the third. Well, in terms of common multiplier, the bottom has 1 times 10 times 10 times 10, but the top does not. There's not a number I can multiply each top by to get to the next top. So this is not geometric. I'm always going to test and see if my series would be geometric first. So this is not. So we're going to try the ratio test. That's always where I'm going to go second. So the ratio test says we're going to look at the limit as n approaches infinity, and I'm going to plug in n plus 1s for all of my n's. And I'm going to divide by the series itself. Well, just about every time I'm going to have a fraction within a fraction. So my next step is going to be rewriting this as multiplication. Okay, now from here, I'm going to rewrite this again. And it's a good idea with the ratio test to kind of put similar things over similar things. And what I mean by that is I'm going to want to group up. Ratio test can get a little like gnarly in all the terms that I have. So I'm going to rearrange some things here. I'm going to make the n plus 1 to the 10th over the n to the 10th. And I'm going to make the 10 to the n over the 10 to the n plus 1. You might be able to skip steps pretty quickly and just go straight to where you have things grouped up because it's just a lot easier to compare what's going on. So now I'm looking at this and I'm trying to figure out what can I reduce? What can I cancel? What powers can I reduce? So let's see. Let me take this first. Well, how can I reduce this? If I have n plus 1 to the 10th, so this is n to the 10th, and then I'm going to have like a something n to the 9th and a something n to the 8th and all these other terms, and this is n to the 10th. Well, remember what we said, these terms we don't really care about. We care about what's happening when n goes to infinity, so we're comparing the degree of the top and the degree of the bottom. Well, the degree of the top and bottom are the same, so this particular little part is going to go to the ratio of the coefficients, so 1 over 1. So this first part becomes 1. The second part I'm going to reduce powers like I did in the last example. So this is going to become 10 to the n minus n plus 1. I'm taking the limit of all of this. Reduce a little more. And I have 1 times, so I have 10 to the negative 1, which is the limit of 1/10. Well, there's no more n's. What do I get out of that? I get 1/10. Is 1/10 less than 1? Yep. So the series converges by the ratio test. Okay, not bad. But here it gets harder. So flip it over. So I would call this part 2. If you're already thinking you don't have enough coffee to make it till the end, there are 3 parts. So we are a third finished for today. Okay, I don't want to just read this to you, but maybe if I don't read it to you, you won't read it. So haha. So the 2 previous examples did not have any x's in them. So that's one thing that they've been easy. They all, when we did the limit, they all had a numerical answer that we could compare to 1. Well, now our series are going to have x's in them. So that means we don't really know if a series has an x in it. We don't really know if the series converges or not, but we can tell the problem, well, if x is between this and this, then the series will converge for those values of x. So this sounds weird, I know. So when you get a problem that's a series that has x's in it, you're not going to be asked, does this series converge? You're going to be asked, what is the interval of convergence for the series? Between what and what value of x will this converge? Because there's some numbers I can plug in for x that will make this converge, and some numbers I can plug in for x that will not. You know, maybe you can imagine that, like, if this is n times x to the n over 10 to the n, and I put a 10 in for x, how is this going to converge? Shoot, where'd my pencil go? Oh, here it is. Don't necessarily write this down, but if x was 10, and now this series is n times 10 to the n over 10, over 10 to the n, well, that's going to cancel, and I'm just going to have a series that's n. So that's going to be 0 plus 1 plus 2 plus 3 plus 4. That's not going to converge. It's going to get really, really big. It's not even a fraction. It's not even decreasing. But what if instead of 10, I put in, I don't know, 1/2? Well, then that means I'm going to have n times 1 over 2 to the n and 10 to the n. Well, yeah, that might get smaller fast enough, get small fast enough that we can find what that converges to. So we can, that would be a converging series. So my point is, depending on what x is, will tell us whether this thing will converge or not. So to figure out what x should be, or what values of x will allow us to have that be a converging series, we're going to use the ratio test. I put a note over here as well. Something else to note, we don't even worry about the nth term test or any other test when we have x's and n's. When they have both in it, we're going to be asked to find that interval of convergence. When they ask us that, the only tests that will work are the ratio and the geometric. So the integral test and direct comparison are just for when they're asking, does a series converge, and it only has n's in it. Once we throw x's in and we want to know where does something converge, we need ratio or geometric. Okay, so find the interval of convergence for this. So we're going to start again with the ratio test. We're going to start by automatically, like, just doing what we know without a whole lot of thinking. So the ratio test says plug in n plus 1 for all of our n's. And divide by the series itself. Well, I'd like to get to the point where instead of dividing by the series itself, so instead of putting the series under here, n x to the n over 10 to the n, just to save space, I'm going to multiply automatically by the reciprocal. Okay, so instead of dividing by the series itself, I'm going to start multiplying by the reciprocal. Okay, I have a whole lot of stuff. What the heck? So let's rewrite this. And let's put same stuff over same stuff. Stuff that looks similar. So like n plus 1 on the top. On the bottom, n looks similar to that. X to the n plus 1 on the top. X to the n looks similar to that. And 10 to the n on the top, 10 to the n plus 1 looks similar to that. So now I have I've kind of grouped it up so I can look at the limit of each thing separately. And that's totally legal. When I take a limit, I can look at the limit of this and this and this and have them all multiplied together. So let's see how stuff reduces. So if I'm looking at the limit, oh gosh. If I'm looking at the limit as n goes to infinity, well, what does this become? This is the same degree over the same degree. So I go to the ratio of the coefficients. This is going to be 1. This, let's reduce. So this is going to become x to the n plus 1 minus n. And this is going to become 10 to the n minus n plus 1. So I'm just subtracting the powers of things that have the same base. Let me rewrite again. Oh, goodness. So I'm looking at the limit as n approaches infinity of x times 1/10. Okay, well, if this is the limit of 1 times x times 1/10, I'm plugging in n going to infinity, there are no n's left. So just like in the last problems, I don't get any n's, I don't have an n, whatever. So what I have left, the limit of this is just 1/10 x. So my answer has an x in it. Well, what do we know about the ratio test? My answer to the ratio test, if the absolute value of the answer is less than 1, the series will converge. So I'm going to say this, if the absolute value of this is less than 1, the series will converge. So if 1/10 x is between 1 and -1, the series will converge. Let's solve for x. Multiply both sides by 10. So if x is between -10 and 10, the series will converge. That's what they're looking for. This is called the interval of convergence. So for any value of x between -10 and 10, if I use that in this problem, the series will converge. So think about, I plugged in 10 and it didn't work. Well, if I'd plugged in anything less than 10, I could have gotten this series to converge. So any number between 10 and -10 for x will make this series converge. This is called the interval of convergence. And that's what they're going to be looking for. Awesome, right? So again, this is called the interval of convergence. P.S. If they're ever asking you for the radius of convergence, which I think will come up in a minute, if this is the interval all the way from -10 to 10, the radius is just half of that interval. So the radius of convergence here is 10. So from -10 to 10, that spans 20 numbers. So the radius of that interval is just half of that, which is 10. I don't know why they make you figure out the difference between interval convergence and radius of convergence, but there it is. Okay. I'm going to pause for 1 second and get a drink of water, and I will come right back.